inductance. A wire of certain length, when twisted into a coil, this is known as inductor. If the current is made to pass through an inductor, an electromagnetic field is formed. A change in the magnitude of the current changes the electromagnetic fields. Increase in the current expands the fields, and a decrease in the current reduces the field. Therefore, a change in the current produces change in the electromagnetic field, which induces a voltage across the coil according to the Faraday's law of electromagnetic induction. You can refer my playlist of EMF to understand the electromagnetic fields. The link is given in the description. Inductance represented with the letter L. Units are Henry. Two-terminal symbol is coil A, B, two terminals L. By the definition, 1 Henry, when current through the coil changing at a rate of 1 amp per second induces 1 volt across the coil, then the current voltage relation gives V equals to L di by dt. Where V is the voltage across the inductor and I is the current through the inductor. Di equals to 1 by L V dt. Now integrating on both sides for this between 0 and t seconds, 0 and t seconds. On left hand side we'll get I 0 to t equals to 1 by L, L is constant, integral 0 to t v dt. Then this one I of t minus I of 0 is equals to 1 by L integral 0 to t v dt. Then I of t equals to 1 by L integral 0 to t v dt plus I of 0. So from this equation we note that the current in the inductor is dependent upon the integral of the voltage across its terminals and initial current in the coil I0. So the power absorbed is P is given by V I, that equals to L I from this equation di by dt watts. Now energy stored, W is given by integral 0 to t p dt. Substitute the value of p, then integral 0 to t li di by dt of dt. So L integral 0 to t I di. Then L, so is I square by 2 for this 0 to t. Then L I square by 2. So energy W equals to half L I square in an inductor, and this is a power in an inductor, and this is the relation between the current and the voltage in an inductor. First conclusion, that V equals to 0 when I constant. From this equation we can say di by dt equals to 0, which means the changing current is 0 or current passing through it is 0. Then it acts as short circuit. Second conclusion, if I is increased to I plus at t is equals to 0 plus, for small change of I, that is nothing but I is increased but t is still at 0, then some amount divided by 0 is nothing but infinity value, then V will be infinity. This is not possible practically. So in a fixed inductor, the current cannot be changed suddenly or abruptly, or inductor don't allow the sudden changes in the current. From this equation we can come to this third conclusion, that if V equals to 0 also, W will be a finite value. The energy W don't depend on voltage V. From this equation, if V is 0, then there is some initial current in it. That current W will be there. Fourth conclusion. A pure conductor never dissipates energy, only stores it. And that is why it is also called non-dissipative passive element. But a physical inductor dissipates power due to internal resistance. That is why practical inductor L is known as lumped element.